So this morning, we're very lucky to have Longo from Gatan, and he's going to talk about electron energy loss spectroscopy. That's the EELS acronym over there. And we kind of touched on this a little bit yesterday. Someone asked, how do we know that this is titanium 4+? This is the technique that's going to tell us that. So we've got 2 lectures this morning on EELS. Paolo is going to give us a broad overview. Then the next lecture is going to be on calculating the EELS fine structure, which is determining the valence of these spectra. And we're going to follow up with more EELS lectures on Wednesday. And tomorrow we're going to stop and do tomography, the 3D imaging.
All right, thanks. Thanks for the introduction. Also, thanks for inviting me and giving this presentation. So basically, this lecture will be just kind of like pretty broad, like about EELS. So you're not going to see much math involved. So it's very general introduction to EELS, which means electron energy loss spectroscopy, and FTEM, energy filtered TM. These are all techniques that we'll demonstrate in the lab over the next few days. So these are basically the topics of my presentation. So we'll talk about some fundamentals of electron energy loss spectroscopy, FTEM fundamentals and properties, some spectrum imaging. So essentially, then you're going to add another dimension to EELS and FTEM. So we have 2 different approaches we can use. So we got the STEM spectrum imaging and also the FTEM spectrum imaging. So you'll be able to build a data cube. And then also we'll do a little bit of advanced acquisition and also processing techniques, data processing techniques like MLS fitting, NLS fitting, and duo EELS. So these are actually pretty important to extract chemical information or to deal with some overlapping gauges. And then duo EELS is very important for chemical analysis and also extended energy range, etc. So you learn how useful duo EELS is. And then I will also a little bit talking about how to optimize the entire system, microscope plus spectrometer to get the best, to get probably the best data for high-speed acquisition. Okay, so electron energy loss fundamentals. You guys have some slides. I think I changed this slide yesterday while I was waiting to board, my plane. So essentially, we have like a thin specimen here. So the specimen has to be thin because we're talking about transmission electron microscopy. So the electrons have to travel completely through the sample. As the electrons travel through the sample, they will interact with the atoms in the sample. And a lot of things will happen. Some of these electrons will interact elastically, which means there won't be any loss in energy. So these are the electrons that we use for diffraction, we use for STEM imaging. Some of the electrons will lose energy as interaction with the electrons in the atoms here. And these electrons, like I said, they lose energy. We refer to them as inelastically scattered electrons. And these are the electrons that we are interested in for EELS. Everything here is, all these inelastic electrons are pretty confined within a narrow angle. So essentially, the advantage of these inelastic electrons, inelastically scattered electrons, is that provided you use a large aperture here, you can collect most of the signal. Okay. Then also, as a result of this EELS process, you can see better from here. So you get the electrons coming down. They will push one of these electrons in the core shell to an upper level. As a result of that, these electrons there will be an amount of energy loss, which is what we measure with EELS. And also these electrons, which was excited, will go back to its original state and will emit an X-ray. Okay? Or I can emit another OJ electrons. So these 2 processes are kind of competing with each other. So in general, EDS is more favorable for heavy elements, OJ for light elements. The other thing that you should understand from this slide is that you don't have EDS if you don't have EELS. So always your primary technique is EELS. You need to have energy loss in order to have an X-ray to be emitted or an OJ electrons, okay? So that's kind of very important. The other thing is that all the EELS signal is confined within a narrow angle and is all forward scattered. So this is actually to look at the process a little bit in more details. So we got electrons coming down. They will push one of these electrons in the core shell to an upper level. It will lose an amount of energy, which is we call it like a sort of delta E, which is the energy needed for these electrons to go to an upper state. And what we measure essentially is the E0 minus delta E. And the E0 is the initial energy. And depends on the microscope you're using. It could be like, I don't know, it could be maybe frame now from like 60 kV up to like 300 kV. I think we're going to have the microscope for, at least for the practical sessions, you know, set up with 300 kV. So we're going to have electrons coming down 300 kV, okay? This is in the case of nickel oxide, just to look at in more details what's happening here. So we got nickel atoms, oxygen atoms, etc. So the nickel is heavier than the oxygen, so has more electrons available for transitions. So if you look at these electrons here, there are 855 eV. These electrons are in the 2p states, and essentially you need 855 eV to bring these electrons up into the conduction band. So at this we actually generate something that we call L2 free edges in the EELS spectrum, okay? So when you look at in the EELS spectrum edges, L, M edges, it really depends on the initial states where these electrons are excited from. So if you still look at the nickel also has other electrons. These other electrons are in free S, free P, etc., free D states. And all these states, actually, all these orbitals will form the M edges. So electrons that will actually start from these levels will form the M edges in the EELS spectrum. In the case of the M edges, which are P, we need a lot less energy, about like 68 TeV, to bring these electrons from into the conduction band. So you clearly understand that if you're looking at the EELS signal from these electrons, it will be in a low energy, because again you need the less energy to pull these electrons out. If you look at 855 eV, the electrons will come from the 2p states. Okay, but you need a lot more energy to push these electrons out. If you look at the oxygen obviously it's a lot lighter than the nickel, has less electrons available for transition. And in EELS we have only one transition, which is from the 1s state. This will form the K edges. So the K edge in this case, which is 532 eV. So you need these electrons to go from this state above into the conduction band. Yeah, so basically you need 532 eV in this case. We'll learn that these electrons can go to different states into the conduction band depending on how these orbitals are hybridized with the other elements. So this is how we get like chemical information from EELS. We'll look at this in more details in the next few slides. The other important thing is the EELS electrons can start from the valence band and into the conduction bands. It will form something we call interband transition, which are pretty well used in the case of study carbon-based material. I think I have one example that shows that. So this is a little bit in general about EELS. So all the EELS signal in the TM results from the interaction between the beam and the specimen electrons. The other, like I said before, EELS always probes primary events. We don't probe any secondary event. So we learned from the first slides in the presentation that if you want to have EDS, you need to have some energy loss. So always EDS is like secondary event, just like OJ. Another advantage of EELS is the signal is very localized. We don't have any fluorescence, which is typical of EDS. Fluorescence is like when EDS travel through the sample and they generate other X-ray. The delocalization is due to the only delocalization that we see the EELS, so true delocalization, is due to the quantum nature of the interaction. We're not going to talk about these aspects in the entire presentation. This is a little bit more advanced. Another advantage of EELS is that we always get information on the electronic structure of the material and excitation. So essentially with EELS you could get chemical information, you could get optical information. And this is what we're going to learn during this presentation. And then you'll see more details throughout the course of this workshop here. So sometimes, we look at the EELS spectrum, we see like a lot of edges. We need to understand where these edges are originated from. So in general, when you look at K edges, so L edges, M edges, and N edges, O edges, this is essentially what we see in the EELS spectrum. And these features, so these edges, essentially in the case of K edges, are originated by electrons in 1s state. L edges, it could be 2s or 2p. M edges, 3s, 3p, etc. So the heavier the atom, so the more electrons has the atom, the more features you're going to see in the EELS spectrum. Okay? So if you look at like heavy elements like, gold or platinum, in general, you look at M, N. You could also look at O shells. So basically like O edges, okay? Because you have a lot more electrons available. But this is actually gives you like an overview where each edge in the EELS spectrum is kind of originated from. So this is an example of an EELS spectrum. So if you look at the EELS spectrum, we always start from the left-hand side. You see this is zero energy, so there's no any energy loss. Essentially, in this particular case, the electrons all travel through the sample and they were elastically scattered. Okay, this is like zero energy. Then we have a feature pretty intense, so we call it this the plasmon, which is the second most intense feature in the EELS spectrum. We'll look at each region of the EELS spectrum in more details in the next few slides. We got the nickel M23 edges. We learned that these are about 68 eV. Carbon K edge, 284, oxygen, etc. And nickel here, 855 eV. If you look at this slide, if you look at this spectrum, you learn that there's quite a change in intensity going from the zero loss peak down to the nickel edge. Okay, this is about 3 to 4 orders, about 3 orders of magnitude in intensity. So there's quite a lot of jump in intensity going from the zero in energy down to the nickel. So you quite need a very good dynamic range in your camera to record the zero loss peak as well as the nickel, and make sure that the nickel has enough counts so you get like enough statistics. So we'll show you later on in this presentation how we actually tackle this problem, and we are able to collect the entire EELS spectrum with a good statistic. We have something called dual EELS. So this is actually a section in this presentation. But this is actually to give you an idea of like an EELS spectrum, how the intensity changes from the zero loss peak, which is essentially elastically scattered electrons, all the way down. And as you move up more and more in energy, you're going to see a decrease in the intensity. Okay. Okay. So what kind of information are we extract from EELS? So we have zero loss peak, where we get. It's important because we can get specimen thickness information. I'm going to show you how in the next few slides. And also the zero loss peak is important as a tool to get like information on energy reference. You can use this energy reference tool. Essentially, if you want to measure chemical shift, you need something to calibrate your spectrum. And the zero loss peak is probably the best feature you can find in the EELS spectrum to do the calibration. Plasmon peaks, which are important if you want to get an information on electron density. Low loss distribution, polarization response, complex delay function. Near zero loss features, we get information on band structure like interband transitions. I'm going to show you one example for that. core loss edges, which are important for elemental composition. Also in this region, we have something called the near edge fine structure, which actually gives you information about the band structure, density of unoccupied states. This is actually very important for chemical analysis. You can also get magnetic information, get quite a lot of information from your sample. Just looking at this near edge fine structure, essentially the first 20-30 eV of after the onset on your core loss edge. This is something that I don't really have much experience with, but some people have been using for just to get like information on sort of long-range distribution information or arrangements for your atoms. So this is called extended fine structure. There's actually a lot of people who work in XPS are actually interested in this type of measurements here. I don't really have any example on that in this presentation. So the question that we ask is how can we analyze EELS data properly and try to extract information? So this is going to be the point of this presentation. So if you look at the zero loss signal, so you can see highlighted in green. So the zero loss signal, you can tell by the name like zero. So essentially, for the most part, is made of electrons that didn't lose any energy at all. Okay. So why is the zero loss peak important? So the zero loss signal or zero loss peak is important because we need to extract specimen thickness information, and I'm going to show you how. So what the software does, you need as an energy reference because say that you're looking at this edge here, and as a result of any chemical interaction, you might have a shift. You want to make sure that you remove all the stabilities, the environmental stabilities in your system. So the best way to do that is to use the zero loss peak as a tool to calibrate your spectrum. Intensity reference, so if you want to get information on the beam current, so you can calibrate the intensity of your CCD and get actual information on the beam current just by recording the zero loss peak, and then also beam current here. I don't know for those of you, but probably you never heard, some of you probably heard about inelastic mean free paths, which is this lambda here. So as the electrons travel through the sample, they encounter different interactions with the atoms here. Some of these interactions we learn will generate, they're like elastic, so meaning that there's no any significant loss of energy. But then there's also other interaction where these electrons here will interact with the core shell electrons or with the valence electron, basically electron-electron interaction. And we'll see some loss in energy. So now what we measure with lambda essentially is the average distance between inelastic events. So as the sample travels through, we'll go through different scattering events, inelastically scattering events. And this actually will define this lambda. Now, this lambda depends on the accelerating voltage that you're using to collect your data. And it also depends on the density of your material, essentially on the atomic number. Now, if you're working, if you are increasing the accelerating voltage, say you're working at 300 kV, this lambda will be bigger, right? So because you're gonna have less, there will be like less inelastic interaction. Okay. If you work with heavy elements, so if you drop the accelerating voltage, say you're going to 80 kV, you're gonna have more and more scattering events. So this lambda will be smaller. Same thing if you're depending on the material you're working on. So you're working with the heavy elements. Heavy elements, you're gonna have more and more atoms. More and more electrons. So you're gonna have more possibility of inelastic scattering. And as a result of that, the lambda will be smaller. So if you look at the probability here, this probability here of a certain number of scattering events, it will depend on the actual number of scattering events. Also depends on the T, which is the thickness of your sample, and the lambda, which is the actual distance here. So for sort of zero scattering, you know that this T over lambda will. So this T over lambda will depend on the I0, which is the intensity of essentially the zero loss peak, so without any energy loss, divided by the intensity of the entire spectrum. Essentially, what we do with when we do with the software is just working out this term, which is the T over lambda. We call it this relative thickness. So the only thing that you need for the relative thickness to work out the T over lambda is the intensity of the zero loss peak, the total spectrum integral, and the local mean free path. But if you add these two terms, you can work out the T over lambda. So the T over lambda for EELS is very important because it gives you like an idea of how much scattering you are getting in your sample. Okay? So if you know your accelerating voltage, you know your material, the software is capable to work out lambda, and as a result of that, you can work out the absolute thickness of your material. Okay? So the only thing you need to know in order to work out the T over lambda is the I0 and the I total. So I0 is the intensity of the zero loss peak integral, and the I total is the total spectrum integral. Okay? So if you just recorded the entire spectrum, you can work out the T over lambda. So T over lambda again gives you an idea of the total scattering of your sample. So basically, just this gives you a little bit of an idea of the lambda depending on the accelerating voltage. So you can see the lambda is pretty high for beryllium, which is pretty light. So we don't have much scattering. And it gets smaller and smaller as you increase the atomic weight. So you can see like the hafnia is a little heavier than the beryllium, more electrons for inelastic interaction. You see the lambda is getting smaller. And also, if you look at the accelerating voltage, the lambda is getting smaller and smaller as you decrease the accelerating voltage. Okay? So the lower the accelerating voltage is, the more inelastic interaction we're going to have in our sample. So if you do like EELS 80 kV compared to 300 kV, 80 kV, we're going to have more signal in the EELS spectrum because we have more inelastic interaction. Same thing happens with EDS. So now let's move on to another region of the EELS spectra, which is also pretty important, is the plasmon peak here. So the plasmon peak in general in a thin specimen is always the second most intense feature. Okay? So the plasmon peak is important because you look at this equation here, it just gives you an idea of what the plasmon peak, which is all these peak highlighted in yellow, can tell you. So you can see that looking at the energy here, you can work out the number of, basically you can work out the electron density. So all these terms are kind of constant. So that's actually is very important because you can get an idea of your material. And we use a lot, the plasmon peak, like especially semiconductor industry, to work out, silicon oxide to bulk silicon, so the electron density will change. It also changes going from conductive to insulators material. And I'm going to show you some example in the plasmon peak. This actually is an example. So we have, this is just a TM image where we have aluminum with some precipitates of aluminum lithiate. So we don't see very much in this, if you look at this image. So we record an EELS spectrum. But if you look at the plasmon peak, in the case of the aluminum matrix is a 14.5 eV, but in the case of aluminum lithiate is shifted down in energy of 13.5. So the way you want to look at this sample fast is basically by doing like FTEM or energy filter TM. So you take an image with using only these electrons here in blue. And then you take another image using these electrons in red. And if you use these electrons in red, you're going to be able to image all these particles here that contain aluminum lithiate. Actually, it turns out there is not something that has been done recently, but we are like maybe last year or 2 years ago, there was a paper published on Science by Matthew Mecklenburg, USC, where he actually used the plasmon peak, the shift of the plasmon peak to work out changes in temperature down to the nanoscale. And it basically developed like a way of accurately measure the plasmon shift. And I think in its measurement, it could get a resolution of 66 millielectron volt. We actually run some other experiments with electrostatic shutter. We managed to get better quality data, actually improve the resolution. So this was done with just a conventional microscope, just looking at the shift, try to interpolate the plasmon, the zero loss peak with the plasmon peak. And it was able to map the temperature down to the nanoscale with pretty good resolution in terms of temperature, and a resolution of probably like a few nanometers in spatial resolution. This is another way of using the plasmon peak. So there's also something a little bit more advanced. If you want to get information on the complex Dirac function, you could use something called Kramer's Kroning. Is also this technique can be used to work out the absolute thickness of your material. I can show you how we do Kramer's Kroning in the software for those of you who are interested. So other important features which are located down here, in general between the plasmon peak and the zero loss peak, these are called interband transition. We learned that these in transition are originated from electrons going from some in the valence band into some levels into the conduction band. And some of these features are actually very important for optical studies. Every time you can relate an optical spectrum, you can relate an optical spectrum with energy loss spectrum. So you can see all these surface plasmon which correspond to different emission of your particles, light emission of your particles. So if you look at this, if you take EELS spectra from these three different regions across your particle, region A, C, and B, so you can see the region A correspond to an emission in visible C, which is right here inside the particle near infrared. You can see that now this is going closer to the zero loss peak, and then also the B here is more on going in towards the UV, so it's basically shifted in energy. You can always, like I said, you can always translate an optical spectrum in an EELS energy loss spectrum, but you could do this vice versa. So let's look at this in more detail. So if you try to kind of map, this each single feature. So you can see if you look at the feature here, the A, which is the visible here, you can see that all this emission is located right at the corner of this particle. These are 1.75 eV, so this is the near infrared. So the other one, 2.7 eV, is located right here across this particle on the side. And here is on the center of 3.20 eV. So this is towards the visible here. So essentially, you can map each single mode in your nanoparticle. You need a good energy resolution. I think this example was done with just a regular Colfeg, so you don't need very high energy. You don't need a monochromator to get this data. But maybe in this is another example. In this case, you need a monochromator. This is actually looking at these different modes in this silver nanowire. This is data that was published from McMaster like 6 years ago. You can see that going across the entire nanoparticle, you see different mode. You get from something from 0.44 to 0.63 V and so on. So you can actually map each single mode. But in this particular case, you need a pretty good energy resolution to be able to distinguish each single mode. Probably this one is very complicated because it's very close to the zero loss peak. Okay, so you have to make sure to get your zero loss peak as narrow as possible. This is actually another example. This is looking at plasmonics in a gold prism of different sites. So this is a smaller nanoparticle, bigger nanoparticle, and you can see that the excitations are different. This is actually doing you can convert again EELS with CL, so you can do everything you can do things pretty simultaneously. But this is actually to give you like another example of looking at these plasmonics using EELS. And since we kind of talked about a little bit the previous example with CL, we also have technology to be able to collect the light coming out of your sample. Essentially, this is an holder fitted with some prism here, some mirrors here, parabolic mirrors where you collect the light. So essentially, you can also collect the light down to the nanoscale with your TM microscope. So now let's move on to the core loss electrons. So core loss electrons, now we're looking at these electrons right here. So basically we are on the core loss region, which in general we refer to the core loss region after 100 eV, okay? So this example here is for, I think this is the beryllium. You can see some interesting structure here. So the shape, all the features in the structure actually will define something we call a near-edge fine structure, which is very important for chemical analysis. And then we have, after probably 40 eV or something, we have something called extended fine structure. So you can see that all these electrons here, all this is sitting on top of decay background. In general, our default in the software is to work out the background is parallel background, okay? So why the core loss electrons are important? They're important for element identification, concentration, and also near-edge fine structure where we get chemical state, and extended fine structure where we get information on the local environment. Okay, how we do concentration with EELS? So concentration with EELS, imagine that you have two elements in your sample. This case, I think, is the boron nitride. So we got the boron edge, boron K here, nitrogen edge here. So the areal density, which is the N here, essentially is the number of atoms per unit square, depends on the intensity of a particular edge. This beta is the collection angle. This delta is not delta. This is basically the integration window, and it will depend on the I0, which is the intensity of your zero loss peak, and then water term, which is we call it this cross section, which the software will work out automatically. It's essentially cross section is just the probability of a certain inelastic scattering for a particular edge, given certain conditions, which is the beta, which is obviously the collection angle, and we'll talk about more the collection angle later on in this presentation. So the only thing that you need to know in this particular case is your collection angle, which depends on the experimental conditions you're using to take your data, and also the integration window right here. And then the software automatically will work out the areal density. And the software also works out automatically the cross section, and it uses like different models. Are we going to do any quantification in this course? We will do maybe something when we'll take some data, some EELS data. I'll show you how the software does the quantification. Okay. All right. So this is actually very important because you can work out the absolute number of atoms. So here you do absolute quantification, but a lot of times people are not really that interested in getting absolute number of atoms. They want to know more like a relative concentration. So imagine that you have two elements, like in this case boron and nitrogen. The only thing that you have to do in this case is the I0 will be the same for both. So essentially the quantification now will be just the ratio between the intensity of element A, the cross section, divided by the intensity of the edge B here, given a certain conditions, and also the cross section. So this is basically IA divided cross section A divided by IB divided by cross section B. So if you're talking about relative quantification, you don't need di0, which is the intensity of the zero loss peak, essentially. Okay, so this is just in summary of all the information that can be provided by EELS. So you are also understanding this very fast introduction that you can pretty much get every single information of your sample using EELS. You can get information, optical information. You'll be mostly focused on these particular regions of the EELS spectrum. You can get information on electron density, complex L-F function, also information on quantification, compositional information, and you'll be mostly focused on this region of the EELS spectrum we call like a core loss region of your EELS spectrum. And you can also get information on the chemical information. You can get magnetic information from your sample. Depending on the information that you want to extract from your sample, you will be mostly focused on certain regions of the EELS spectrum. Do you have any questions on this? Yes?
Can you give any comments on what the error is in the quantification?
So the error depends on many factors. So there's an error which depends on the elements, the edge that you that you're using. Say that you're using like K edges. So K edges are basically originated by electrons for the 1s state. In that particular case, the software give you like a pretty small error on the K edge compared to other edges. Other factors, so it depends again on the type of edge that you're looking at. So K and L edges give you the smallest amount of error. But there are also other errors that will come from the particular environment or matrix of your material, particularly if you're looking at some elements are overlapping, some edges are overlapping. So you might have an error there. Depending on which window you're integrating, and also the way you are extracting the background. So that could also cause some errors. So it's pretty, you can refer to the actual cross-section, but then there might be different situations where the elements overlap. So it could go from like 5% to a lot more than that. It could be like a few percent to a lot more than that, depending on the situation, whether the elements are overlapping with each other. And also depends on how thick your sample is, because you have to extract the background. So I don't think I'm going to touch base, but there's also, in addition to signal to noise ratio, you have to consider signal to background ratio, which changes with the energy of your sample, also changes with the conditions that you're using to acquire the data. So it's, if you can, you can refer to like the actual cross section, and then I can give you like a number of so what the model that we're using to work out to calculate the cross section. So there's an error in there, but things could get a lot worse, depending on different situations, depending on elements overlapping, etc. Yes.
So I was wondering on page 15, the shoulder in the peak next to the plasma peak, is that a second plasma peak, or is that an edge actually? And why is it not taken into account in the integration?
Here?
Yes.
So the second plasmon peak, it could be, actually this is a second plasmon peak, yeah, you're right. So you can see that this is actually removing completely the zero loss peak. You're doing something called deconvolution. You basically remove this peak. So in general, as your sample gets thicker and thicker, you get more and more inelastic scattering. You form several plasmon, and then all these plasmon kind of converge into one big plasmon. When you look at very thick sample, and I looked at very thick sample where you don't see the zero loss peak anymore. You just see the plasmon. Only, yeah. So the distance between this point and this point is the same between this point and this other point, which is the second plasmon. So if you work with a thin specimen, you're not going to see the second plasmon. Yes.
So when are you calculating thickness from zero loss peak? So you are calculating total intensity of the spectrum. So by total intensity, what do you mean? By the intensity of the edges or the intensity of the whole spectrum?
Yeah, let me get the slide. So basically, what the thickness does, we did the information the height 0, which is essentially like just a zero loss peak intensity. Okay, so here in green, and then you need the total intensity of the total spectrum. But in general, you don't actually measure the entire spectrum. You just measure, I don't know, the first few hundred of EV or the first few tens of EV, because the intensity is going to be, is mostly in a thin specimen, the intensity is dominated by this region. So you're not going to see much of a difference in that case. Like in FTEM, when we do like a thickness in FTEM, you take an image using only these electrons and another image using with a slit out. So essentially, you take the entire all the electrons.
And a follow-up question. So if you have, say, an element hafnium and hafnium oxide, your sample is varying between these two. So how do you calculate lambda in those two cases?
So the software, so what we use to work out the lambda, there's something built inside the software. That is the easiest way. So you need to work out they call it the effective atomic number. So say the hafnia, I don't know, 60 something. So if you do hafnia oxide, you have to do the effective atomic number. So the software automatically works, especially in the new software, automatically works out the absolute, it works out, the concentration. So from the concentration, you can work out the effective atomic number, and then from there, your accelerating voltage, your experimental conditions, and then you work out, the software works out the lambda, and as a result, the absolute thickness.
It assumes the software assumes that you're dealing with a free electron gas, and with the free electron gas, there's some rules that you can use to make guesses at what the scattering density was in that free electron gas. And what you're hoping is that the error is a logarithmic in what actually this thing was, because it isn't really an electron gas. So the approximation is good for materials that have band structures that look like free electrons, and they're pretty terrible for things that are not. So they'll misbehave for d electron systems and f electron systems, and they'll do a very good job for things like silicon and aluminum.
Yeah, sometimes it gets close, sometimes it's like very far. So it's actually very important when you work out. So you can work out the areal density like easily, but the problem is when you want to go down to volumetric density, that you need the absolute thickness value, which depends on the lambda, and then you might get errors on the lambda. So you have to be a little bit careful on that. Was someone else? Yes, you.
This technique can be used for metal coordination compounds. And regarding that, how can the relative quantification can be performed?
So you said that you want to use quantification to get chemical information.
Yes.
Yeah, so that's you could do that. Say, so say that you're looking at silicon oxide. So you could just do the quantification and say, okay, it's got silicon oxide. But I think there's a more elegant and more precise way to do to tell that you have silicon oxide just by looking at the shape of the EELS spectrum. So the fact that you have silicon oxide that will it will influence the shape of a near edge fine structure, the fine structure of your silicon L edge or the silicon K edge, and then from there you can tell absolutely that you have silicon oxide. So when you do quantification, you might have a passivated layer with oxygen, but you're still assuming that the oxygen is bonded to the silicon, but it might not be the case. So it's always it's always better to just look at the shape, because the shape you get chemical information. Quantification, you don't know how these elements are interacting with each other. A lot of times, especially when you look at oxygen, you might have a passivated layer on the surface, and that could cause changes. Yes.
My question referred to page 26. When you talk about atomic ratio, you talk about we can identify isotope also, or just like if you say, okay, I have this amount of silicon in.
Yes.
I mean, you talk about different atoms, so you can also identify isotopic ratio.
No, I mean, here you just look at different, the ratio, say that you have atom A, atom B, H A, H B, or atom A, atom B. Yeah, then you do the atomic ratio, so they're basically the relative amount of each element in your sample.
It's not sensitive to isotope, right? You're looking at electronic excitations. So the mass of the nucleus doesn't come into these equations.
Yes.
Does the relative quantification of the atomic ratio, does that require calibration standards like EELS?
No, but you can definitely work out the relative quantification using standard. I mean, that's what I did for my PhD. So I was working with, I had to quantify gallium, oxygen, and gadolinium. So then I built my standard, came up with my sort of we call it like conversion factor. And then, you could do the quantification, but it just works in the same way. Essentially, you're doing IA divided IB, which is the intensity across this edge B, and then the intensity across the edge A. So their ratio is proportional to the amount of the relative amount. So you can work out through standard your conversion factor, or you can use calculated conversion factor, which are essentially the cross sections. But you can do exactly the same thing with EELS. Now, if you use a standard, you have to make sure that your data is always acquired in the same way. So you don't change anything in your microscope conditions. So you're working with the same accelerating voltage. You're working with the same, basically like the thickness is within a certain range. And also you want to use the same background window, the same integration window. Everything has to be exactly the same. But I was getting, actually, going back to the quantification error. When I was doing my PhD, I was doing all the quantification through standard. I was actually getting very, very good results, a lot better than using calculated cross-section. But you have to make sure to use always the same conditions, always. You might have, we were having some deviation depending on the thickness of your sample, so you have to be always within a certain range. So you have a lot of constraints, but you could get like pretty good, you could get like pretty accurate results. Yeah, you have different ways, but it works out just like EELS. Actually, we'll talk about EELS and EDS later on, and then we'll compare quantification with both techniques. All right, let's move on to the FTEM, otherwise we're not going to finish on time. So what is FTEM? FTEM is actually these days, a lot of people are moving towards a STEM-based technique, but I think there's a lot you can do with FTEM. And it's actually very important that you guys have the possibility of doing both, like EELS and FTEM. So what is FTEM? Imagine you're starting from this nice TM image. And with FTEM, you're going to add colors, so which will make it look a lot better. Each color will correspond to a certain element. Okay? So what is FTEM? So FTEM in general is contrast enhancement technique. So we use it to improve the contrast in images, diffraction pattern, and a lot of people, and actually we are selling a lot of camera at the end of the filter just to remove the inelastically scattered electrons. Remember, for the very beginning of this talk, I'll show you the EELS spectrum. We'll talk about elastically scattered electron, which means that zero loss peak, electrons in the zero loss peak area of your EELS spectrum, and everything else is like inelastically scattered electrons. It turns out that these inelastically scattered electrons actually reduce the contrast of your sample. So basically, they make your image kind of look blurry. And then you remove that, and then you actually increase the contrast. And this is why a lot of biological people in life science, they actually use zero-loss filtered imaging just to improve the contrast. It can be used as a mapping technique, so you can create some elemental maps and also chemical maps. And then also it can be used as analytical technique. In general, you do that in a mode called FTEM spectrum imaging that I'm going to show you later on. Okay, so that's what happens inside the microscope. Everything starts inside the microscope here. So this is, in general, in the conventional microscope, this point, which is, we call it like a projector crossover, which is a crossover point, which is a differential pumping aperture inside the microscope. It's right above the sort of viewing screen. So what we do, we take this point, and we project this point right here onto this, right after the prism. So we have an EELS spectrum here. So now what we do here, the electrons will go through the prism and will be dispersed in energy. So everything is pretty mixed up here in terms of energy. And then they go through the prism and they will disperse in energy. So now we have an EELS spectrum which is projected like this. There's an aperture here that we'll show you later. And then what you do, you take this point and then use a series of lenses to magnify or demagnify. Okay? So now we have an EELS spectrum here. We project, actually no, we have some electrons, some energy loss electrons here. They go through the prism, they will disperse in energy. So we have an EELS spectrum here. Then we take this EELS spectrum, we use all these lenses, and then we'll project onto like a CCD and then for display. Now you have an EELS spectrum here. Okay? So now we are in spectrum mode. But also, and you always have an EELS spectrum here. But then, you know, what you can do is you can use these lenses to convert this spectrum to an image. Okay? So now we have an image. This is actually an image with electrons that lost any energy, every amount of energy. So this is the equivalent of just a regular TM image. Okay? So right now you're using the camera at the end of the filter as a camera to record the TM images. Very expensive camera because, you know, it's at the end of the filter. But you want to do a little bit more. So you want to say, okay, I have an EELS spectrum here. I'm forming this image. So now, now you're like, okay, I want to create an image only using these electrons here. So electrons that didn't lose any energy. Okay? So elastically scattered electrons. Essentially, you insert a slit, and you take only these electrons here. And then so you will let only these electrons go through, and then you'll form this image here. So now this image is made of electrons that didn't lose any energy. So we call like elastically scattered electrons. Obviously, it's not entirely true because the slit in general is like 10 eV, so there's always some energy loss in there. But for the most part, you can see how the contrast is increased. You can use that to create maps. We'll do this in more details during the practical session on the microscope. So you can create a nitrogen map, oxygen map, copper map. This is pretty well automated in the software, so there's not really much to learn in here. But you can see that it's taking 3 different images, oxygen post-stage, pre-H1, pre-H2, and it uses these 2 images to work out the background, and they extract the background from the post-stage image. You get this image here. All this image we call a map because the intensity is proportional to the absolute amount of that particular element in this particular region. So essentially, you can convert this intensity map to compositional maps. You can put everything together, you get colors. So the good advantage of FTEM is, first of all, that you're in TM mode, so you don't need STEM. That could be a big advantage, especially for those beam-sensitive material where they don't stand the high density, the intense probe. So you can do everything in TM mode. You can actually, in a relatively short amount of time, you can get information from a very large area of your sample. Okay, so we already kind of introduced that. The FTM has many uses. Contrast enhancement technique. You can get zero loss filtering, most probable loss imaging, contrast tuning, pre-carbon imaging. Probably you never heard about pre-carbon imaging, but this is very well used by people in the life science field because it's used to actually kind of remove the effect of the carbon in your image. Everything is made of over 90% of carbon, so you have to try to do everything to kind of remove the effect of the carbon in your image. It can be also used for elemental mapping or jump ratio mapping. We got 3-window method, 2-window method, and also it can be used for chemical mapping. That's an example of a nice image. I don't know what it is. It's a sunny side-up egg. But you could see that going from this point to this other point, the contrast is increasing just because this one is unfiltered image. This is using all the electrons, so with all the energy, inelastically scattered electron. We put a slit in, just like we did before, and now you can see how the contrast is increased. So if you look at all these features here, they're a lot more better resolved than in this particular case. So if you're looking at fixed sample, probably like just using zero loss filtered images can give you a big help because the thicker the sample, the more inelastically scattered electrons we get. So if you can remove their effect, you will get a benefit in the contrast. And also a good thing is if you have these two images, unfiltered and zero loss filtered, like we did before, you can work out a relative thickness map, like our T over lambda map. So you can do that in FTM as well. It can be used for diffraction. So I guess you want to do diffraction. When you do diffraction, you want to remove the effect of inelastically scattered electrons. So there's actually a lot of interest of doing doing like diffraction in just recording your diffraction pattern zero loss filtered. So you can see, you look at all these features inside all these reflections here, you can see that they're a lot better resolved when you remove the inelastic scattering electrons. Okay, let me show another example here. So imagine that you're starting from, this is an unfiltered image. This is actually a biological sample, so it's a cell. So this is an unfiltered image. So now this is a zero loss filtered image, so we are putting a slit across the zero loss peak. So we are taking only elastically scattered electrons here. So you can see that now we see more features in the sample, we're increasing the contrast, and you can keep moving in energy. So, and then just, like using these as a mean of increasing the contrast in your sample. This is actually one of the best examples that I like for just to demonstrate FTM or energy filtered imaging. This is actually this is a polymer, so we get like, this is a polystyrene with polyethylene. So actually this is a polyethylene with polystyrene. Both materials are made of exactly the same atoms, carbon and hydrogen. So if you put them together, you're not going to see anything. But the polystyrene has double bonds, carbon-carbon. So, and then you will form an interbond transition at 7 eV. So imagine you put like a slit at 7 eV, and then all of a sudden you see these polystyrene particles. And this sample actually is very tough because it's very beam sensitive. It's a polymer. So you can actually probe a very big area in a matter of seconds, like 8 seconds. So FTM has advantages. In this particular case, we're using this as a tool of increasing contrast. So now we're doing something to increase the contrast of these nanoparticles here of polystyrene. It can be also used for do plasmonics, but you need a very stable slit. I also need very good energy resolution. This was done in Graz using a monochromated TF20 with a very, very small slit. So you can see the slit of 0.3 eV. So that means that mechanically your slit has to be very stable. So in general, the slit is made of 2 plates. So one is fixed and the other one moves, okay? So it's piezo controlled, and it's basically the movement depends on the energy, depends on the accelerating voltage. I think at 200 kV on 1 EV correspond to 1 micron. So if you want to move, if you want to get 5 EV slit, that means that you need to open the slit by 5 micron. And then things will be different at different accelerating voltage. But again, you can use that to work out the different optical modes in your silver nanowire. So you can get like data which are comparable with the McMaster data from the same sample. But this was done with a much older microscope in F10 mode. Okay, so how do we get maps? So in order to get maps, we can use 2 different ways, because you have to remove the background. If you want to do quantification, maps means that you're getting something that is proportional, where the intensity is proportional to the composition. So we could get like, we can use like 2-window jump ratio mapping. You can tell by the name that you're just doing a ratio between 2 different images, or 3-window maps, okay? Or you can get like a series of images. So we call it this spectrum imaging. Hope we have time to talk about spectrum imaging. I don't think we do, but anyway, so how do we do ratio mapping? So ratio mapping, you have to take 2 different images in energy. So you get one center. So this is the case of vanadium. So on the software, you just type vanadium, and automatically the software will come out with some default conditions. So you get like a vanadium L edge, which is 513 eV. So essentially, you're taking an image, a filtered image. This case is using a slit of 30 eV, and is centered at 513. So you're taking this image here, and then after that, you change the energy, you take another image, this image here, which is the pre-edge image. What you do, you take this image, you do the ratio between these 2 images here. So the ratio obviously will increase the contrast, and so you essentially increase the contrast. But the problem of this particular technique is that there is no a compositional map. So the intensity is not going to be proportional to the amount of atoms. If you want to do something more quantitative, you have to use this approach, which is called the 3-window method, where you take 3 different images. So one is across the post edge here, so this image here. Then you change the energy, you take a pre-edge 2, the pre-edge 1, and then you use these 2 images to work out your background. So once you work out your background, which is the image here, this image down there, then you just do the ratio between the post edge and the background, and then you get this light, you get the background subtracted post edge image, which actually is pretty important, and that is proportional to the number of atoms. That's an example. Secondary phases EELS, it just gives you the amount of elements in there. And you can see the scale. This is a very small scale. So actually, F10 is pretty good if you want to do low magnification studies, and it's also relatively fast. Also, chemical phase. Yeah, that's taking nitrogen, carbon. You see here in the case of nitrogen, you're taking 3 images. Image post edge, pre-edge 1, pre-edge 2. Same thing you do for carbon and oxygen. And the software can be set up in a way that you just select all the elements. You can just click start and then come back and find all these elements, all these maps with assigned colors. You can put them together. Chemical mapping. Yeah, so this is data that I took in using the system in Pleasanton. This is looking at lithium iron phosphide. This is an electrode. And so basically, they were studying the performance of this battery, looking at charging, putting this battery over several cycles. So they wanted to know how much lithium was left in the electrode. So instead of just looking at the lithium, we went to look at the iron, just an example. So if you have lithium iron phosphide, the iron is N2+. If you have iron phosphide, it's iron 3+. So there's a chemical shift of 2 eV. So the spectrum doesn't look great, but just because it was done in FTEM mode. So essentially, we did FTEM spectrum imaging. So you scan your slit across a certain energy range for like 680 to 730, and you just look at the chemical shift of the iron L. So good thing is that you can probe a very large area with a parallel beam, and in a matter of minutes. This was done in 4 minutes. Okay, specimen information from FTEM. So essentially, FTEM can be used as a contrast enhancement technique, most probable loss images, contrast tuning, pre-carbon imaging. You can also do elemental mapping. We use free window method or jump ratio imaging, and it can be also used as a chemical mapping tool. So essentially, you can use FTEM just like you use spectroscopy. All right, spectrum imaging. So this is a little bit more advanced. I'm sure I'm not going to make it to 160 slides, but you guys have all the other remaining slides. I don't think I'm going to make it to the end. But okay, so spectrum imaging. So what is spectrum imaging? Spectrum imaging is actually a little bit advanced, but this is what used to collect and store detailed information in addition to spectroscopy information. So look at this example here. This is a data cube, and what we do is you basically have spatial information, X and Y, and you also have energy information, okay? So this is what spectrum imaging is about. You have 2 different approaches for doing spectrum imaging. So one is the STEM SI or EELS STEM approach. So here you take an EELS spectrum. So the energy is constant because you're acquiring the EELS spectrum in parallel. And you just scan the spectrum point by point, okay? This is called the 3-dimensional spectrum imaging, where the X and Y are changing, are the 2 dimensions. The 3rd dimension is the energy. The other approach is the FTEM approach. So now we are in TM mode. So you are the beam is parallel. So X and Y now are constant. The only thing that you're changing is the energy. These are 2 different methods that can give you the same information, or they should give you the same information. This is a parallel acquisition of your EELS spectrum. In this case, is a serial acquisition because we actually change the energy. A little by little, you're actually adding an energy plane, okay? But like I said, you get to the same result in the end. So let's talk about the STEM approach first. STEM approach is actually the approach that is the most common these days because people are moving more and more towards STEM-based technique. It's also like the STEM approach has some advantages. Simultaneously, you can collect a different signal. You can collect EDS, CL. If you have a CL detector, you can build your STEM image point by point using a dark field detector, in addition to an EELS spectrum. So what you do in this case, you take an image like here, you divide the image into a series of pixels, and you scan the beam pixel by pixel. And you collect a pixel by pixel an EELS spectrum in parallel. You can collect an EDS spectrum, CL spectrum. Point by point, you're also building your STEM image, okay? That's an example, very large area. You take a STEM image, take like we call this a survey image. You select, you define the area where you want to scan the beam. You want to scan the beam across this area inside the green box. You define the exposure time. You define the pixel size, and then you start the acquisition. And then you can see point by point. You can extract the EELS spectrum. You see different ages here. So here we got oxygen. From here, there's also some silicon. Look how the shape of the silicon is changing, going from here to this position to position number 2, I guess. So you can see the shape is changing. And if you go also On number 3 is also again different. So you can see how the silicon is changing. So the chemistry of the silicon is changing. You can see here we're getting like oxygen here. This is typical of silicon oxide. This might be something else. This should be the nitrogen. I think this should be the nitrogen edge. Yeah. Yeah, this should be the nitrogen edge, and then you're getting some sort of silicon nitride in there. And number 2. So essentially, you get an EELS spectrum point by point. Okay, you can move around and extract spectra from different regions of this data cube here. You can also use the software. This is from the new software that you guys have installed in your Quantum downstairs. Oh, it's another building, right? In another building. So you just select all the elements here, and automatically the software will work out the distribution of each single element across the area of interest. And the software can also do quantification as well. F-time spectrum image approach. This is, in a way, is equivalent in a way that you end up with an EELS spectrum, pixel by pixel. But like I said before, in this case, the beam is in parallel mode because we are in TM mode, and you just change the energy plane by plane. So essentially, you are building an EELS spectrum. In this particular case, it's like a serial collection. Okay, so this is how we define our F-time spectrum imaging. So you just select all the elements, click this button here, automatically the software will come up with a good energy range, and then you just acquire this. Image, all these images plane by plane in energy. And then what you do, you end up with an EELS spectrum. You can treat that just like regular spectroscopy. We'll do this in the lab. But you can see as you move around, you collect different EELS spectrum. You can see different ages here, and you can create color maps as well. You can also do this to study like plasmon shift, or to study some sort of chemical phases. This example, you can see that this is a silicon oxide in this region, and this is a bulk silicon. You can see the second, I think this is the second plasmon here. The sample getting a little bit thick. But you see the shape of the plasmon is changing, going from silicon oxide to bulk silicon. And there's also a chemical shift of a few EV. So you're going from 24 EV to 17 EV. And I can tell you right away, if you're working on silicon, this is silicon oxide, this is bulk silicon. So you don't have to do any quantification. This is actually the fastest method to do any sort of chemical analysis. They call like just looking at different chemical phases. It's very well used in microelectronic industry because people are interested in silicon and silicon oxide. So right away you can tell that this one is silicon oxide, this is bulk silicon. Okay, let's move on to a little bit more advanced stuff. So this is doing MLS fitting, so which means multiple linear least square fittings. This actually can be used for a number of reasons. So imagine you record the spectrum here. So the spectrum here is made of two components. Component A and component B. So all these are overlapping. So you can easily extract the intensity from component A. So you can just put like a very narrow integrating energy window here. But what about this component B? Okay, because you don't have enough space to fit the background. So this spectrum actually is made of two components, component A, component B. So you can look at the formula. So this is the fitted spectrum. It's made of background contribution plus model A. So you see like the reference spectrum A multiplied by a scaling coefficient BA, and then also the reference spectrum B multiplied by a coefficient. So what you want to do is you want to be able to extract these model A and model B. So essentially you want to extract the component A and the component B and actually map the intensity of their distribution pixel by pixel. So what you do is, in this particular case, you need to have only reference spectra. So if you have reference spectra, you feed them, automatically the software will work out the scaling coefficient. And from the scaling coefficient, actually looking at the latest version of the software, we'll be able to work out the quantification, so the composition, okay? So let me just show you one example real fast. Okay. So let's look at this as a chromium oxide. This is actually a good example because you fit the background right before the oxygen. You see the oxygen pretty nicely, but the chromium is like sitting right above the oxygen, so right after the oxygen. So you can extract easily the oxygen, but what about the chromium? You can't really put the background before the chromium. Look what happens if you put a background before the chromium. It goes negative. So you're getting some negative counts there. So this is actually an error. It's going negative counts, so wherever you have oxygen, you don't have chromium, it's going to go negative. The oxygen, you're good. Essentially not that good, but you can use a very small integration window, like in this case, and then perhaps avoid the chromium contribution. Okay? So we want to be able to separate these two components, and we use for that MLS fitting. So if you move around the sample, you can find different areas. So you can find an area where there's pure chromium, an area where there's pure oxygen. Or you can go use the database in the EELS and the EELS atlas. We're actually working on improving the EELS atlas, and I think you can submit your spectrum on eels.info, and then in theory, we are supposed to put it in the software. I'm saying theory because, the idea is that once we build a more reliable database, then people will be able to do quantification, and also this MLS fitting.
Oh, you're going to screen them. Which spectrum is right?
Yeah, we have to check that, so that's the other problem. So we got some people submitting spectrum. To be honest, I don't know what, I mean, in this case it's ray twisted. I don't know what it's doing with this spectra, but in theory, the idea is to put it like in the software, and then it will do like MLS fitting and all the stuff. Instead of using sort of cross-section like we do in model-based approach that we have in the new software, we use like a real standard, always scaled based on the actual spectrum. And then, but the problem is that you have to make sure that they're giving you the right conditions, so collection angle. Actually, accelerating voltage is not a problem because I don't think you can make a mistake on that, but the collection angle can be a problem. Then once we have the accurate information, then we can sort of scale or recalibrate based on the conditions which you want to use this particular standard spectrum, the standard spectrum. But yeah, that is the idea for on short-term idea, I think. Okay, so what you do essentially, you just take a reference spectra from oxygen, chromium, and then the software automatically will work out this scaling coefficient B, BA, a scaling coefficient BB for say the two different ages, and automatically you can tell you're going to work out the coefficient 0.4, 26 for oxygen, 0.3, and then essentially this is how you work out quantification, and these two ages are actually overlapping with each other. Okay, so you can see now the maps is more accurate. Let me jump these. Another example, actually no, let me go to this, I don't have much time, but let me go to this example here where we have silicon with different phases. Look, we got silicon, bulk silicon here, which is a 99 eV, silicon nitride, which is about 103 eV, a silicon oxide. All these have different ages. You also have chemical shift. So you can extract from different areas of your sample reference spectra. So here we have pure, this region we have pure silicon, bulk silicon. Green region up here, we got silicon nitride. Here on the side, we have, on the edge, we have silicon oxide. So the software automatically will use MLS fitting. I'm going to show you in the lab how to do MLS fitting, so don't worry about that. And you'll be able to work out the same map, the same distribution.
This is often due to decompose of multiple scattering?
I'm not sure in this particular case. But yeah, you can remove the...
Because it would have a very big effect on the shape of that energy.
Yeah, so depends on how you define the integration window for your MLS fitting. In this particular case, I would probably stop around the 110 EV, or you just remove or you do the deconvolution. So sometimes, like not everyone acquires the data in dual EELS mode. But like you said, in this particular case, you probably don't want to extend your integration window too much unless you remove the plural scattering. So this is an example from the Antwerp group where they managed to map down to the atomic level the manganese in different oxidation states. I think they had to turn the monochromator on. I don't know how much on, but it was on. And then you can see that you have different manganese state. You can see the edge here that is actually changing in shape and also in position. And you can use MLS fitting again to work out the position of each single atom. And it will be different because there's some changes in the chemistry down to the atomic level. Non-linear least square fitting. The difference with the previous example, that it was MLS fitting. In this case is non-linear because the models in this case are function, are not static like in the case of MLS fitting. Okay, so this is also built in the Gatan software. So what we do in this case, long story short, we use this NLS fitting to work out chemical shift, plasmon shift in particular, everything that has a Gaussian shape. It's also used to get chemical information. If you want to do a ratio between edges, especially in transition metals, because they all have Gaussian shape. Like an example here. So here we're interested in mapping the shift of this plasmon. So you do this NLS fitting. You can see the red one is a nice Gaussian fitted to this plasmon peak. And then what the software works out, it works out the amplitude, which is the intensity, full width of maximum of this Gaussian. It will also work out the center. So point pixel by pixel, this plasmon will shift, and the software will work out exactly the position of this of the plasmon peak at each single pixel. And you can see how this plasmon is shifting in energy, going across the entire particle. All right, EELS and EDS together. So we already showed this slide here, but EELS and EDS, like I said before, you need to have EELS in order to have EDS. So you always have these two together, okay? So why don't acquire them together? So if you look at the composition, with EELS, now especially with the latest generation of detectors, we are pretty uniformly efficient with the Z, so we can collect both light and heavy elements. EDS, we saw before that it becomes more and more becomes stronger and stronger as the weight of the atom increases because we have more inelastic scattering. Okay. So and also there's a competition with Doge spectroscopy that is more favorable for light elements. So EELS is good at verifying unknowns, but EDS has actually an advantage on that because you can collect. You have less problems with the background, so it's actually pretty good at identifying unknowns. So if you don't know anything about your sample, I would probably do EDS. It would be my first, would be the first thing I would do. EELS is really good with thin sample. It's actually really good on when the sample is when the thickness is like 0. Say that you're looking at 2D materials. They are only 1 atom thick. And EDS, you actually get quite a lot of signal as the sample gets thicker and thicker. Chemical mapping, we get chemical information using EELS because we look at the shape of the edge. But in the case of EDS, you can always, you can only get chemical information just by doing compositional analysis. So you have to do composition first, and then from there you can extract the chemical information. In EELS, I showed you some example. You can get information, optical information, chart, you can get pretty much everything. You can even work out the band gap using EELS. These are all information that you cannot get using EDS. This is actually data, just just do it like EELS and EDS together. This is using the FEI chemistem. This is EELS using just a regular quantum. You get palladium and gold. You're getting everything together. You notice like in EDS, you see this peak 8 kV. So this peak is basically the copper Ka line, which comes, you don't see in EELS, you see in EDS. The reason is because EDS, the signal is not localized. And this is because the sample was dispersed onto a copper grid. So you're getting a lot of signal, a lot of X-ray from the copper, which you don't get in EELS because the signal is localized. Well, let me skip this part. Okay, quantification using EDS. So the problem of doing quantification with EDS is that you have absorption, right? So absorption means as the X-ray travel through the sample, they are absorbed. They can be absorbed by the TM holder, they can be absorbed by the detector, or they can be absorbed by the sample itself, okay? So there's been like a lot of development on EDS side with better TM holder, so better, with high visibility TM holder, so just to minimize the absorption effect from the holder. And also now we are working with windowless EDS detector, so there's not really much absorption from the detector itself. But the main problem comes from the sample. So as the EDS, the X-ray travel through the sample, they absorbed by the sample itself. So this is actually very important. This kind of limits the quantification using EDS. And this is actually, this absorption is mostly affected by this low energy X-ray. So essentially this X-ray from light elements. So what is the solution? So people have been spending a lot of time on trying to model this absorption. But in general, the best way is actually to use one single detector and try to tilt the sample towards the detector. So if you do so, you're going to increase the number of X-ray reaching the detector. Now there are a lot of geometries, so people are moving towards multiple detectors, and that becomes very complicated to study, to model the absorption, because each detector is going to see different X-ray. So the best way, people have reported completely different quantification using each single detector. So the best way is actually to turn 3 detectors off, 2 detectors off, and tilt the sample towards the other detectors so you can increase the amount of X-ray reaching those 2 detectors. So if you do quantification, this is actually comparing EELS with EDS, and to some extent they are similar. I mean, in EDS, you always work out a relative amount through a conversion factor, which is called the K factor, as the K factor is calculated theoretically in the software. But you can also calculate experimentally, and there are ways in the software to do that I can show you. Do you have EDS here?
On the F20. Some of them will use it.
Yeah, so if I use my GMS3, but we made a lot of improvement on the EDS. I can show you how the software the software does all these calculation. And we already looked at quantification using EELS. But if you compare these two, there are 2 terms. Actually, there's 1 term in each equation that is theoretically calculated. We got the K factor in the case of EDS. We got the cross-section in the case of EELS, okay? So in the case of EDS, the K factor will depend on the accelerating voltage, ionization of fluorescence term, detector contribution, which is the solid angle, and the atomic weight. In the case of EELS, the cross-section depends on accelerating voltage, convergence angle, collection angle, and atomic weight. So this is just to compare the factors that contribute to the cross-section. So this is what you have to do in order to set it up your EDS quantification. You need quite a lot of information, solid angle, etc. Also information about the detector itself. EELS, the only thing that you need to know is the collection angle and the accelerating voltage. So it's a lot more straightforward, I think.